Thank you for letting me talk in this nice activity. And so this is partly a review talk, and then in the later part, I will discuss some recent developments. And so the topic is not new. I mean, I started this with other people exactly 30 years ago, and but I keep working on it from time to time. And recently, I think I made some progress, so I want to tell you about this. But first, I have to review something about the quantum effect and the way the symmetry manifests itself in the bulk and the edge. Okay, so when it goes to the edge, you can say something about the conformal field theory you have to the in the edge, and then we try to see how it extends to the bulk to some extent in the bulk with the boundary. So it's half-plane geometry. Let me remind you some basic facts about the quantum effect. For example, if you feel completely the first Landau level, then you have a droplet with roughly constant density, okay? And because this is a radial view of the thing, you see that these red dots are field orbitals, Landau orbitals, and they are all field, and so they all together make this droplet density, okay? And the main point is that there is a gap in the bulk, and so you cannot have density waves in the bulk. So you say it's an incompressible fluid. However, at the boundary, you can have fluctuations. And if you look to the one particle spectrum, you see that there is this is very degenerate here, okay? But then at the boundary, because of some containing potential, the degeneracy is broken, and you realize some sort of Fermi surface, okay, here. Because this is also momentum and but also radial dependence. So this is this sort of thing, and then you have a sort of Fermi surface in real space, and so you can consider particle Hall excitation of the fermion, and you can also take a linearize the spatial relation, and so you get a relativistic fermion. It's a charge and chiral because of the magnetic field, the waves only go in one direction. Okay, chiral 1 + 1 dimensional fermion. How can I realize this fermion? Well, at first you can simply say, okay, let me fix the radius to the boundary. Then I remain with the angular dependence, okay, and then I have a 1 + 1 dimensional. The 2 + 1 dimensional fermion become a 1 + 1 dimensional, immediately become a 1 + 1 dimensional fermion on a circle, and so it's conformal theory, okay, with central charge equal to 1. Then the picture extends to fractional feelings. You say, okay, in order to understand that there is a gap also for fractional values, fractional filling, then I have to imagine that the Coulomb interaction is very important. This is a non-perturbative effect, so it's not cannot be solved ab initio. So you say, okay, let's suppose I have again an incompressible fluid. Then I have to look for interacting fermion on the boundary, but I know how to treat interacting fermions on the boundary by bosonization. And so it's still a central charge equal to 1, but you change the compactification radius of the theory, and then you can describe also fractional filling on the edge by so-called chiral Luttinger liquid or chiral boson, depending on. So that's a basic thing about the phenomenology of edge excitation in the conformal field theory. So the question is, which kind of conformal theory I can use for general fractions, not just this Laplace state that we saw before, which have clearly C equal to 1 simple conformal theory. Well, in principle, there are endless possibilities because you can have a multi-component abelian, you can have a abelian times some coset for neutral excitation, many things, because just the condition that you have a conserved charge, it doesn't tell you much about what the theory is possible, what the theory would be. So there are endless possibility, and however, experimentally we know that there are not so many plateaus. In fact, mostly these so-called Jain states, which are a two-parameter extension of the fractional of Laplace state for n equal to 1, they are the Laplace state. For n bigger than 1, they are other states. Okay, and so how do we deal with this? Well, there is this. There are many physical inputs in this, and one main feature is that there is a correspondence between wave function and conformal correlator, but this time in the plane, not in the boundary, in the plane. Okay. Yes. What happens at the integer of the edge? There are many components of a Weil fermion. Just expand like before, and you get many component Weil fermion. Okay, that's I mean, straightforward limit you can do. Okay, and then when you have interaction, so the simplest idea is to use this U1 to the N theory. Okay. But it has a lattice of charges. It has a lattice of, it has many parameters, okay? So in general, this UN theory has an n-dimensional lattice with n square half parameters, root the weight lattice. And so this is too general. This is already too general to describe the thing. So anyhow, with the help of many ideas, Haldane pseudopotentials, and so people have been able to pinpoint some relevant conformal field theory and to make an extensive model building that lasted about 20 years. I would say till about 10 years ago, and which has experimental confirmation. So that's a very nice application of conformal field theory. So my question here in this talk will be, is it possible to derive this conformal field theory just from symmetry principle? So some sort of a priori derivation, okay? And to some extent, yes, and this has to do with extending the conformal field theory with this double infinity symmetry of quantum incompressible fluids. So this is some extended symmetry which encompasses conformal field theory, and to some extent determine here at the edge, more or less uniquely, well, not really uniquely, but somehow indicates what are the Jain states, and then we see it's also useful to understand some property of the bulk. Okay, so what is this double infinity symmetry? Double infinity symmetry is the symmetry of the incompressible fluid under area preserving diffeomorphism of the plane. So because you have that the density is constant, the number of electrons is constant, so the area is constant, okay? So area is constant. So the fluctuations of a droplet are just a deformation of the droplet. We keep the area constant, and you can realize them by a change of plane coordinates in the plane, which has a unit Jacobian or unit metric, determinant of the metric is remain 1. Okay, so in infinitesimal form, this is the condition. Okay, so that's okay. Is because to lead in order, the determinant of the metric is 1 plus the trace. Okay. So, so I can say that I realize the fluctuations of the incompressible fluid in terms of this change of coordinates of the plane. Okay, so the fluctuation of the fluids are described by the generator of this symmetry. At this point, you have to remember from your mechanics course that this is indeed the canonical transformation of a two-dimensional phase space. So if you consider X and Y like coordinate momentum, a canonical transformation is exactly a area preserving diffeomorphism. That means that I can realize it in terms of Poisson brackets, like this. In fact, this is a way to rewrite this condition, okay? Poisson bracket, which involves x and y, or z and z bar, which are complex coordinates, okay? And so, and L is a scalar function, which is a generator of transformation. So a generic scalar function of z and z bar, which describes is a generator, okay? Generating function. So I can realize this this transformation with Poisson brackets, okay? So this is a classical algebra, and if I take a span in a polynomial basis of z and z bar, okay, I define this generator as components of this general function, then they obey the so-called little double infinity algebra, which is a classical algebra. Okay, so this is the classical algebra. There is a question? No. And okay, and so for example, how do I describe the fluctuation of the boundary? Well, the fluctuation of the density by the chain rule is simply the Poisson bracket of the density with the generator. If I do this, okay, if I do this, I know that the rho is a kind of circular step function. So derivative will produce a delta function, okay? So you see that the fluctuation is at the boundary, is localized at the boundary for r equal to square root of n, and then what remains is the phase of z and z bar, which combine in this wave, okay? So that's, you see, a very simple derivation of the fact that a fluctuation at the boundary is a wave propagating on the boundary, okay? Then we go to the quantum theory. So quantum theory, you have to know that in the lowest random level, the coordinates are not commuting, okay? This is this thing. So simply we replace a Poisson bracket with commutators. And this is so-called magnetic length that which is expressed in terms of a magnetic field. And so we put it to 1 because it's, we use a dimensionless units, okay? So at this point, the generators are simply one-body operators, one-body form of operators of classical theory, okay? So then you could compute the algebra. The leading term is a classical term, but there are a number of higher order terms. Because, you know, when you take a derivative of derivative, when you take a commutator of derivative square, you have several terms, and then so there are a finite number of terms, finite known number of terms, which involves higher power of a h bar. Okay, but anyhow, this is completely known expression. Okay, so the idea of using this symmetry in the quantum effect, in fact, was not new, and so there was this famous paper by Girvim et al. Plasman. They use the momentum basis, so which is sort of generating function of this polynomial basis. And if you use these generators, momentum generators, the algebra takes a more compact form like this. Okay. However, this form is not very useful. What is useful is a polynomial, because polynomial on the ground state obey very clear conditions. For example, if I apply to the one generator to the vacuum, I realize the fluctuation we saw before for n bigger than m, because that creates a party-Hall excitation with a positive momentum, okay, positive angular momentum or positive momentum on the edge. Vice versa, if I apply with n less than m, this makes 0, because I'm trying to make a party-Hall excitation inside the Fermi sea. That is impossible. Okay, so that's a basic ground state condition that fits with a conformal field theory, as we shall see. And so in this basis, we understand not only the algebra, but also representations, because it's not enough to have an algebra. You should also find which are the representations, okay? Because otherwise it's mostly useless. So, yes?
What is the structure of the storms OH2 or H3 in terms of L as a linear in L or
No, no, polynomial.
polynomial.
Polynomial of higher order, yes, because this
higher
is
order, not
yeah, yeah, yeah. It's, they are known. You can in principle expand this, you know, and obtain from this closed form, and you get this.
But this looks linear in raw.
No, no, exponential is polynomial. Polynomial, when you expand the series, there is a problem of normal ordering here, which is a technical point. Anyhow, it's non-expression. So that's so this W infinity symmetry is a dynamical symmetry. So some excitation relate the vacuum, and other generates all the excitation, exactly like conformal field theory. So it's a sort of extension of conformal field theory. Okay, let me notice that you have this with equal weight, equal indices, they mutually commuting. So they are conserved charges, which in fact correspond to moments of the density, as you can see from the definition. Okay, so these are kind of conserved charges associated to a certain representation. Okay. The problem with this setting is that it's not useful because it needs some normalization. So this is a first quantized picture, okay, no, quantum mechanics, but we want to go to relativistic limit. So you have to remove the effect of the Fermi sea. So you have to invent some renormalization. And in so doing, as we know very well in conformal field theory, for example, if you discuss by fermion conformal theory, you have to normal order the thing, and then out of this you get a central extension. So this algebra should be supplemented with the central extension that's coming from the thermodynamic limit or relativistic limit. You put as you like, okay? And so this setting is not by itself really useful, okay? Because you have to get around these very diverging expectation values. Okay, so what we did at the beginning was just say, okay, let me just represent the same operators on the conformal theory of the edge. So represent the same operators, but only with respect to the theta angular dependence. So I forget about the R. I fix the radial dependence. Then this quantity is an integral on the edge. There is a factor of R in front, but just the power. So I just remove by scaling. And so this is a representation of the same operators directly on the edge. And you see the dependence on n disappear, and I can study this as is just a free Fermion analysis, okay? And so what do I get? Well, I get C equal to 1 theory, so it's just current algebra, Virasoro, but I also get higher powers, which is called enveloping algebra of polynomial operators, which is particularly clear in boson inversion, because boson inversion, you start by saying you have a scalar field, and you have the current is d phi, the stress tension is d phi squared, that we know very well. But then in this theory you have a W3, which is d phi cube, then d phi fourth, and so on. They are all these conserved currents and conserved charges of the W infinity symmetry. They are all well defined once you do normal ordering of the vacuum and usual stuff, okay? And so this is for C equal to 1. This is a very simple. You would say, okay, that's okay. This is just current algebra, okay? Current conformal theory of current algebra, okay? Then you take a polynomial of the current algebra. So what do you gain? Well, you say, well, you gain nothing, okay? Well, no, that's not true, because at this point there was this work by mathematician Katz and Radul that classified completely all representation of this polynomial algebra on the circle, on the space of the circle. And in fact, there are some surprises from representation theory. There are some degenerate representation. Yes, please.
The difference between this expression you have here for the generators and the one on the previous page is just the ordering of the arguments.
Yes, yes. There is a normal ordering, but also I dispose of the R dependence. You see, here you have a integral in R also.
Oh,
Okay, so instead I fix, and then R is one of the variables of the problem, and somehow I have to, because expectation value of powers R grows like n, I have to take care of this. While we will return to this, but there requires some normalization that at that point, that was in the 90s, I could not find the way to deal with this. So if you work directly with the fermion on the edge, then this R dependence is you get rid of it, and then you proceed like an usual conformal field theory by normal ordering. You solve all the problems. Okay. Okay. So the point is that this double field on the edge is not completely trivial because there are the general representations. And it turns out that the general representations are in fact useful to describe the Jain states, the Laplacian and Jain states. So that brings me to this double infinity minimal models. The point is that, as I already said, in general, the double infinity representation are just multi-component abelian conformal field theory with central charge equal to n. And in this case, there is a n-dimensional lattice of conformal dimension, and so you have to specify the so-called compactification space. And so there are many parameters, but there are special points in which this lattice contains leads to external symmetry, UN symmetry, because part of the lattice is the same as the root lattice of SUN. So some of these lattices have a particular extended symmetry. This is a well-known fact of conformal field theory. Sometimes there is an extended symmetry which is level 1 affine SUN like this, okay? And so in this case, the double infinity representation are degenerate. And if I want to use a irreducible representation, I have to do this cosect. So I have to remove SUN symmetry. And so if I do this construction, so if I use only this, if I go, you know, it's slightly in the minimal models. This is not a real minimal model, but the philosophy is the same. Go to the irreducible representations. Take a minimal amount of representation and go to this, define the theory with this reduced representation. Then you find that this in fact corresponds to the Jain filling. And it matches what phenomenologically represent the prominent plateaus observed experimentally. Okay, and what is the physical meaning of this projection? Well, this projection is realizing because you have this SUN symmetry, then you have n equivalent layers. And so, because you projected this away, then you're left with just one excitation out of n. So there are many. So in particular, there is only one electron excitation instead of n electron excitations, which is kind of mysterious property of this of the abelian theory. So there is a reduction of number of degrees of freedom. And so in this sense, we call it minimal, because you project down to a reduced representation, and then you reduce the number of the degrees of freedom. Okay, you take a minimal quantity. Okay, and so there are reduced multiplicities, and also yes, please.
So can you remind me what's the hat?
Hat is affine algebra. Okay, so if you do conformal field theory, you have like a current algebra, you have affine, no, because you have a Fourier mode. Okay, and then if you take the SUN algebra, then you have affine SUN algebra, in which the usual Cartan generators they have a mode index. Okay, they have a mode index. Then there is a complete classification of these affine algebras. And there are some peculiarities, some selection rule. For example, the possible value of the weights are limited to a finite region. You know, maybe you know that when you have SUN, you have a certain chamber, no, where you have all the weights. This is a wedge. Okay. In the affine theory, there is a maximal value. So there is a maximal value to the spin, a maximal value to the weights, okay? And then there are selection rules and many properties of affine. So in general, affine SUN has C much bigger, but level 1 can be realized by abelian fields. So it's just an extension of extension. And then you can project this way. So there are some features of yes, please.
The extended symmetry. Could you repeat what that is? So you first have a you want like n copy of you want.
Yes.
And then.
Yes.
And what do you mean by doing an extended symmetry?
Because it depends on the lattice. Let me explain. Yes. When you have an abelian theory, you have abelian fusion rules. Okay. So, for example, you have a field phi with some charge, I don't know, n, and then m, and then the fusion rule is phi n plus m. So now, if you do for many components, this charge form a vector. Okay, it's still abelian. So you ask yourself, what is the possible general solution of this addition of vectors? Okay, is a lattice. Okay, so n should belong to a lattice lambda. Okay, should be an element of a lattice. So, for example, two-dimensional lattice. Okay, you have some generators like V1 and V2. And then you know that n is m1 v1 plus m2 v2. Okay, so for points of this lattice, the points of this lattice are the general solution of these fusion rules. Okay, so the theory is characterized not only by C equal to 2, but by this lattice, the weight lattice or charge lattice. Okay. And the conformal dimension is the norm. So the n square is the conformal dimension is in general n square over 2. Okay, is a metric of the norm of the vector. Okay. Okay, so there are many theories. Then you discover that V1 and V2 should obey some integer condition because of property of the system. So V1 and V2 are also integer in something. Okay. Okay, but then so the theory is characterized not only by the central charge but by this lattice. Sometimes this lattice has an extended symmetry because it contains the weight lattice of SUN. Okay. For example, if you have okay, for example, if you have U2 can be U square can be U1 cross SU2. So within this lattice there is a root lattice of SU2. Okay, or maybe because this has dimension 1 and this has dimension 1. Okay, maybe it's simpler if we discuss 3. Okay. Okay, inside this lattice, in a proper basis, you find the two weights of SU2. Okay, so in this case, you have an extended symmetry. That's a standard conformal field theory business, extended symmetry, but not the most general extended symmetry. It's a standard symmetry with level 1. Level 1 means that there is a cutoff on possible representation, as I was saying. So, okay. Inside this lattice, for example, two-dimensional lattice, there is a sub-lattice, which is a SU2 lattice, the usual one with the roots, okay, and which have angle 130 degrees, this type of thing.
Yeah, no, I just, because SC3 is a subgroup of you
Yes,
three, so
yes,
I guess I'm confused about the word extended, because it's like. Okay,
yes, yes.
so it's kind of an emergent property.
It's an emergent property. Yes, 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 yes. And rational conformal theory, there are all these kind of nice tricks. Okay, and it's not the most general SU2. Oh Jesus, SU2, SU3, SU3 representation you may get, but you get one. So, for example, you will get that in order to get SU3, you have to find J alpha 1 and J alpha 2, which are the two things, and they're represented by some vertex operators, e to the I alpha dot phi, which by chance have dimension 1, and so they are conserved charges. Okay, with some special vector here. Okay, the same for G2. So within your fields, within your vertex operator, you find generators of the extended algebra. Okay, so in so doing, I get very close to the Jain states. I also provided a derivation of Jain wave function, but it's not complete story here, I would say. And because the problem is that when I do this construction, what I end up with is not a rational conformal field theory. And so that's getting into the limit of conformal field theory technology, and then so this some
It is the correct answer in this is that you found using this W infinity in normal effect. Do you think these are the correct CFTs, or do you think they're not quite correct?
I think they're correct, but I need the experiment or a numerics confirmation,
Okay.
and I don't have both.
But the fact that they are not rational, maybe it's just the fact of life. Why do you use this as a drawback?
No, it's fine. It's getting difficult to study. Okay, getting difficult to study, and so I didn't go very far.
But Andrea, usually we shows that finite number of quasi-particles.
They also have a finite number of quasi-particles. Yes, yes.
I have another question.
Yes.
I think it's a question that we should be discussing for years now. So you make really an exact equivalent between the layers. So you say, for instance,
Not really.
Yeah,
No.
okay.
No, not really. They're not really equivalent. So this I work. I have another slide, but it's getting very technical, and it's getting very technical. So anyhow, I match to the wave function derivation by Hanson and some other people, which they rewrote the Jain wave function very explicitly. And then the layers are not equivalent. But I can deal with it, okay? But it's getting more difficult from a conformal field theory point of view. So I mean,
But I also think the layers are not equivalent. You would not expect non-linear.
no, the electron does not have abelian statistic. That would be a mistake. But excitations.
No, I mean about the excitation.
Excitations, I mean, from conformal field theory analysis, they have a non-abelian statistic.
Case, they don't have non-linear.
Do you really sure? Are you really sure? From the wave functions, from the study of wave functions.
I mean, there is, of course.
Yes, quasi-electron. As a whole, they don't have abelian statistics. No, my as a whole would have abelian statistics.
Yeah.
But I put a question mark. So question mark. You see, I put a question mark. So I'm not completely sure. No, they have. It seems that they have non-abelian statistics. Yes, it seems that they have non-abelian statistics, but I'm not completely sure.
In what sense?
In
what sense non-abelian?
Because the diffusion is not the following. For example, you have Okay. Then I have to.
So moving them around, something in the ground state.
They are associated to this SU.
What you say, ground state?
No, not for the electron. The electron, the ground state degeneracy.
Not a being specific.
Yes.
Move you around in the ground state.
Yes.
Space.
Yes. I don't know. That's the honest answer is I don't know because it's getting a complicated conformal field theory. The matching
That's
with.
what non-abelian is.
Hmm?
Basically, non-abelian means like I specify the position of the quantum particles and moving around, and I change my abelian just means I pick up a phase. Non-abelian means I'm actually.
Yes, there is a degeneracy. Yes, that I can compute. There is a degeneracy in the n particle wave function. There is a degeneracy. So the transformation is not just a phase, but a unitary transformation in this degenerate basis. It is there, yes. It is there because this when I do the projection, this number becomes weights of SUN, and so in general the product of representation of SU2, for example, can have many components. Here you have other terms because you sum up two spins, but it is not finished. Okay, so it's the matching with the Jain wave function, which would be sort of supporting, is not clear, and also what is relevant, what is not relevant in the Jain construction is debatable. This law is something experimentally checked. Okay, it could be checked. For example, now they have measured the fractional statistics.
Much more easily with the numerical calculation.
Yes, that I have not done. Yes, but I have not done it. Yes.
But these people have done these kind of calculations, right?
Not clear. Not people have seen in Jain wave function in numerics that ab initio numerics that there is no degeneracy in the quasi-particle wave function.
P particles bound to two fluxes, which may or may not be co-prime, but in this you can tell it's authority they co-prime or not. So you have the 1/5. Then if you have a five-fold degeneracy, you're abelian. Be non-abelian, you would have to have a larger degeneracy.
Yes.
And so pretty
yes. Okay. Yes. I'm not aware of numerical experiment with such a precision. To answer.
You see the degeneracy.
Yes.
So it's not a question.
Yes. Well, I think now these numerics can be done. What I did
Done for 25, 30 years.
Could be done.
They were done at least 25 or 30 years ago.
They were done. You say they were done?
Yes, about in the 1980s.
For Jain states?
The two-fifth state, yeah.
Okay, so you're saying that I missed some relevant literature of 20 years ago?
Early 90s, mid-1980s.
Okay, then we have to discuss because.
I mean, you know what the degeneracies are.
Okay, maybe,
Yeah.
maybe, yeah. Maybe you're right.
It's not a major question.
Yeah, so just want to make sure you're really in Jain state or just mean some state at the same big bang, right?
Yeah.
Yes, of course, it could be could be the different state, a different state with the same finite fraction. Yes, and then it becomes a problem of energetics.
Positive from your state, that's what that function explains. It's having that theory. We know it's abelian and so on.
You know it's abelian?
Yeah,
There are non-abelian states. I mean, a redesigned state, for example.
Well, Riedrezai is a different story.
And you do particle observation, when a redesigned state. But actually, we know the two-fifth state is not that.
Okay, then you have to show me this literature that apparently I missed. Okay, so let's keep going. Sorry, it's getting late. So I skip this. No, sorry. Yes, please. Sorry.
All possible choices are target.
Sorry?
All different choices are target.
Yes.
So you have to go to a Singapore or whatever. Can you go from one place to another place without going to a Singapore?
This is not a question I can answer. This is just assuming that I have a plateau. So I'm not discussing how to go from one plateau to another. This is restricted to the idea that you have a plateau. So otherwise, all this thing is not working. So you cannot answer what happens when I go from another to another plateau.
Maybe we can ask the question: what is the generosity on the story of the non-repeating
Yes.
What is it?
I don't know. I don't know. Yes. What I did was a derivation of a comparison which seems to fit with the Jain wave function on a disk. And so that's why I explain, I say that there is a derivation of Jain wave function with some extra conditions. And that was the most I went to this, okay?
Z and when and Z or instruction, right?
Is a project.
The K matrix.
The K matrix is the same. The K matrix is the same, but then you have to project states. You have to remove this multiplicity of the layers. So you have a K matrix. In this case, it's very symmetric as a permutation symmetry. Okay, of the layers. You remove this. You project down this. Because that produces a reducible representation of this W infinity. And when you do this, the theory is no longer rational, and then there appears non-abelian quantum numbers, and so the fusion rules becomes non-abelian. A technical property of conformal theory. It cannot be explained in simple physical terms. It's a technicality of conformal theory. Yes, I gauge out some, this multiplicity is gauged out. Yes, you can see this as a gauged Jain-Simon theory if you want.
Why?
Because it becomes irreducible. So as I said, I take a minimal choice of minimal amount of degrees of freedom. That's the idea. Key minimal models. You go down to the simplest model. Yeah, it's getting technical. In fact, I will skip the next thing with explanation. Okay, now we go to the bulk. Okay, so this analysis of the edge is okay. It has left some question mark, as you just pointed out. But let me now discuss a recent development in which you want to understand also the bulk of the Hall effect. So some sort of density waves which exist in the bulk. Okay, and the question of this bulk dynamics is whether this is some sign of universality. So somehow there is indication that there is, of course, a bulk spectrum which is very high energy, but somehow there is a low lying states which maybe have a simple universal theory. Okay, you are going beyond conformal theory, so you are going beyond the topological Jain-Simon theory. You have to introduce some dynamics in the bulk. Okay, so there have been many attempts. Okay, which are here. This is a picture of Jain numerics. And this, I think the points are experiments. The funny thing is that if you have 1/5, you get a minimum, which is called the magnetorotor minimum. And if you have 2/5, you get 2 minima. And if you increase the numerator, you get several minima. And in hydrodynamic approach, and Haldane suggested there is degrees of freedom, which is a two-dimensional unimodular metric, and so on. So that maybe this fluctuation correspond to higher spin, like the simplest would be spin to degrees of like a metric of spin to excitation, and I think there are numerical evidence for this. And so, because W infinity has this higher spin currents, I said maybe I should consider W infinity again and see if I can say something about the bulk. And the answer is yes, to some extent. The crucial idea was to reconsider the dependence on R, okay, and do a Laplace transform, okay. Because the density of the droplet is positive, in R square is definite on the positive real axis, I do the Laplace transform. So then at this point, the Laplace transform has very nice features. I can do the normalization of this large droplet limit. I can do normalization very easily. So it solves my problem of how to go to very large droplet without having all quantity blowing to infinity. And then I also understood more clearly what is the limit to the edge. The limit to the edge is the limit in which I go for coordinates near the edge, which is R. I make a small deviation, but at the same time, I also take values of momenta which are limited in this range. This is the range for which the dispersion relation is linear, so linearization of the dispersion relation. And so this is a combined limit of momentum and position. So I can do calculation doing this limit straightforwardly and get the earlier conformal field theory on the edge, but also the R dependence of more general or R dependence completely. Okay, so and the point is that because this algebra has the powers, they have this higher spin current. The quantum number of the higher spin currents are the moment of the density. And this extra information, I reconstruct the dependence of R. So it's a 1+1 dimensional setting of the Hilbert space, but because in 1+1 dimension I have this infinitely conserved current, and they reconstruct the R dependence by the weights of these moments of the density. Okay, so I can study this Laplace transform, compute quantity, then transform back and get the R dependence. So for example, this is a party hole excitation, and this is the shape of the density fluctuation for the party hole and for the charge excitation for 1/3 state. And this is the form of the shape. And notice there is this funny scaling with the square root of m, which is the denominator here. So not 3, but which would be kind of intuitive in some sense, but square root of 3. So there is a square root scaling with the denominator, not. Okay, so this is the shape of edge excitation. So together with the phase, there is also a density fluctuation at the edge. Okay. The point is that because its edge effect is small, so it's 1/r, it's order 1/r. So that doesn't tell you anything about the bulk. It disappears when you take a very large drop. Okay. So, but then there is. I can go beyond. I can extend the limit. So the previous limit can be extended, and consider a fluctuation within the same setting. I can extend to fluctuations which allow me to define a finite momentum around the edge and in the bulk. So K and P are two momenta on the edge and in the bulk, which are finite when I send R to infinity. Okay, I can extend the setting to allow myself excitation which have a finite extension in the bulk. And the algebra takes a very simple form in this limit. It's all straightforward computation, just applying this limit correctly. Okay, you see that there is the plasma given in donor plasma term, which is the same, but there is also a central extension, which is coming from taking the conformal field theory extension and expanding in the proper limit, you get this factor. And of course, this factor is changed completely the rules of the game, and so you get so it's very important. So you cannot neglect the central extension. And also I can do in the same limit. I have to introduce a potential in Hamiltonian for the bulk fluctuations, and I take, for example, short range potential, which is most natural, for example, for Jain states. Sorry, for Laplace states. And so that's in the same limit. It takes a very standard looking expression. Okay, is density. Okay, so at this point I have all the elements to do analytic computation because I have the algebra, I have the action of the algebra. I know the action of the algebra on the states. Okay, I know the Hamiltonian. I can do. The point is that this is becoming non-linear, highly non-linear, and so I cannot solve completely for the spectrum of H. I can only make ansatses. So what I did, I compute energy of some ansatz which are natural from the previous analysis. That is charge edge excitation and edge particle excitation. So now I will describe some effects which are nonetheless near the edge, because I computed some answer states, so I cannot do a complete analysis of the spectrum like a conformal field theory. So this is much more difficult. So I take some states and see what I get. So this is just to show you that there are these finite effects at the edge. For example, this is a well-known fact that the Laplace wave function has a bump at the boundary which does not disappear. This is numerical analysis. Does not disappear as I increase the size of the droplet, and this is the kind of effect that we are discussing. And so this is the shape of a particle excitation. I have computed analytically, and this is the shape of a charge excitation to show you that is a sizable effect that does not disappear like when I take very large droplets. So it has a finite limit. Okay. Okay. So what can I describe? I can describe this effect of so-called edge reconstruction, which has been discussed many times. The point is that this fluid, you know, there is this tendency to move at the boundary a shell of density at finite distance, because the two-body with repulsive potential has also a small attractive exchange term. So there is a tendency to move a little amount of matter in a thin shell outside the droplet. Okay. Some people say that at the boundary, this fluid tends to melt somehow. So there are numerical evidence of this. Okay, and so I can show this effect by the fact that in my analytic energy spectrum, I have a dip at a finite value of distance and also momentum. I have a dip, and this is momentum of the fluctuations, and also as a function of density of momentum in the orthogonal direction. Okay, and if you want, this picture is nicer because I have introduced the linear term, and so that would be the conformal field theory range, which is linear behavior. Now we are in extended range where you see nonlinear effects, and you have this dip, which has been also called edge rotor, but has not to do with the rotor. And then there is also a non-trivial dependence. No, sorry, the non-trivial dependence with respect to momentum. If I do a charge excitation, if I put a charge excitation, then there is a non-trivial dependence on momentum. There is some fluctuation that extend in the energy spectrum, some fluctuation that appears inside the droplet as a function of the momentum orthogonal to the droplet. Some fluctuation that appear but then disappear as I increase the charge of this thing. So what do I make out of this? Well, these are sort of answer states that describe some physics of the bulk, but near the edge. So it's not really the bulk very deep inside, but some effect at the edge, but finite with finite extent. Okay, so it's not an edge effect, but it's a bulk effect near the edge. Okay, so then I'm coming to the conclusion. So there is this conclusion of the second part, okay, that I can describe the shape of edge excitations, and there is this square root of M scaling that kind of not obvious, and then I can do analytic calculation in so-called half bulk physics. So if you want half plane effects, okay, and so my conclusion, my philosophical conclusion here is that the derivative field approach is just a non-relativistic bosonization, because if I stay on the edge, it is relativistic bosonization. But if I go beyond the edge with this extended range, it's also non-relativistic bosonization. And so I think it should somehow be the same as composite fermion picture in some more algebraic approach. Okay, so what to do next? Okay, the point is that my real goal would be to describe this excitation deep in the bulk. So in particular, this magnetorotor minimum, we're supposed to correspond to spin 2 deformation, and the point is that these are a reference to numerical work, a recent numerical work that support this. So my plan is to see whether I can do with the proper choice of answers, maybe the same that use in numerics to get some analytic result, and then also this there are some open. Of course, these approaches tend to the Jain states and numerical checks, other numerical checks of what I proposed. These density profiles, and of course, if I take a torus geometry, then probably the algebra is completely different, and so I don't know what to say.
Very much. So we have lots of questions already, but maybe we can take 1 or 2 quick questions, and then we can chat more. So I think.
So do you get that? I mean, do you get any extra fundamental anomalies at the edge besides the versor?
No, the same. No, it's because is this central extension is what I get on the edge just once I do this Laplace transform and I use information of extended of this higher spin currents. It's all issue from conformal field theory thing, just rewritten in the proper variable without the singularities, so finite thing. So
the comments in the K matrix theory, the ground state degeneracy on the torus is the equivalent of K. But not the idea that you're not abelian if you degeneracy compared to that.
That's the question of before. Yes. I don't know.
The value is determined for K in the matrix theory.
Yes, but this is all fit in the rational conformal field theory approach. When you go beyond a rational conformal field theory, you're not sure of anything, because the underlying theory is Chen-Simon that tells you all these things, And underlying theory is not just if I compute things, but not from general arguments. General arguments are under the hat of Chern-Simon theory, and rational conformal field theories. So this is not a rational conformal field theory. So cannot jump to the conclusion. I have to compute. On the torus, no.
Okay, I think we'll stop here. So, but now let's thank Andrea again.
Thank you.